Good, thanks, Hugh. I'd also like to thank the organisers for the opportunity of giving a talk here, particularly at Trinity College, which has got such a distinguished history. And also, I've picked up a bug somewhere between here and Sydney, so I'll stick near the microphone and hope that my voice lasts until the end of the talk, and I apologise for the fact the talk will be even less endurable with my voice than it would have been if I was able to speak properly. And also this is joint work with Matt Farr, part of a project that we're trying to work on with respect to time symmetry in various ways. And the talk revolves around a particular experiment. So I'm going to skip a normal introduction and just introduce the ingredients for the experiment, really, to sort of set up the nomenclature. So the first half dozen slides are going to go over some well-known ground. And you can probably tell from the title of the talk that we're going to be making some fairly ambitious, two ambitious claims actually. So we welcome any comment that says you're wrong or that you're not even wrong, because at least if we are wrong, we'll be able to stop thinking about this and go on to something different. But hopefully it's correct. The first ingredient that will be involved here is quantum tomography. We know from yesterday it was noted that if you just have one copy of a quantum system and you do a measurement on it, you don't find out very much at all about the state that the system's in. But if you have a sufficient number of copies of the system, then you can do a set of measurements, let's say the Pauli matrices are as an example, and collect the data for those measurements, one of which is performed on each qubit at random as they go past you. This is called quantum tomography. The results are recorded and put in a computer, and the computer manipulates them in such a way that it spits out the result of the state for that collection of quantum states that you've done the measurements on. And so we would have prepared all of those states in the state zero. If you prepare them in some other state and take the same quantum tomography data and record it, your computer will come up with the state that you've prepared again, which looks like that in the same basis that the first state is expressed in that slide. We'll also be concerned with maximally mixed states, as the last talk was about as well. So that's the symbol that I'll use for maximally mixed throughout the slides. Let me also note that I'll probably call these quantum systems qubits because it's easier to refer to them that way, but there's nothing in the talk which is confined to a two-dimensional Hilbert space. So for a maximally mixed state, we prepare equal numbers of two orthogonal states, and we can do quantum tomography on that set of qubits as well, record the data, and then we'll always get the maximally mixed state, which looks like that, just numbers down the diagonal of the density operator. We can prepare the maximally mixed state in a different way, equal numbers again of orthogonal states, and record the data, and we'll get the same picture in this case for the maximally mixed state. We'll also be concerned with states of sub-ensembles. So if we look at that slide and we remember how we prepared the zeros or ones, we can pick out that set of runs, you know, like maybe 113, 116, 118, in which we prepared the qubit in the state 1, and we just then do quantum tomography on that subset of runs, and it will give us back the state 1. And similarly, if we do it for the plus or minus case, pick out the runs where we prepared plus, then quantum tomography will magically give us the state of that sub-ensemble. I'll just mention here quantum steering because I want to mention that again later as well. This is another way of sub-ensemble selection. This time, once again, we're dealing with maximally mixed states, but we produce the maximally mixed state this time as the reduced density operator of an entangled pair. And let's say we prepared the system in the singlet state, the most commonly used one. Let Alice perform some measurements on her qubit in the 0-1 basis and send the information about when she got the zero state forwards in time to Bob. Of course, the quantum tomography data's been sitting in the computer, and we can do the analysis any time we like. maybe the next day or the next week for that matter, pick out the runs in which Alice got 0, and we find that Bob has got a sub-ensemble in the state 1 in that case. So this is sometimes called quantum steering, and I'll refer to that later. We'll also be concerned with sub-ensemble states of pairs of systems, so then we need to take the quantum tomography data on both of the qubits, let's say in an entangled state. Both of them will be maximally mixed. If we construct the joint state of the two qubits, it'll be maximally mixed as well. But we can select one of the outcomes of the ensembling operation, the entangling operation, there. Let's say we picked out just those runs in which the singlet state was obtained, and we sent that information forwards in time to our computer for analysis. Then we'd get the singlet state for the state of that sub-ensemble, of course. We're getting closer to the experiment that I want to describe. But first of all, I need to just talk about entanglement swapping. In this case, we produce a pair of qubits, once again entangled, this time in the state phi plus, which is an isometrical state as well, like the singlet state was. That's qubits A and B. Qubits C and D are prepared in the same state. And then bits B and C are entangled. And the next step is to perform quantum tomography data on the other two qubits that are involved here, A and D. They'll be maximally mixed, of course. And their joint state will be maximally mixed. And if we select out those cases where the singlet state was obtained for the entangling operation on B and C, I'll just, for the sake of clarity, mark those runs with stars. The lower ones haven't happened yet, but I'm assuming that they will produce, using hindsight, I'm saying that we'll have a set of runs which produce a singlet state, and we can identify them for all 4 qubits. And if we send that data forwards in time, namely those runs for which a psi minus was obtained, and do the quantum tomography, then we'll see that it's in the singlet state. It occurred to me after the first talk yesterday that at this point you might like to take your favourite theory of causality. I don't pretend to understand causality, Matt does, but at this stage take your favourite theory of causality and ask yourself, assume the quantum tomography data is in the forward light cone of the entangling event of B and C. If we looked at the 2 qubits that come out of the entangling event, they'll be obviously entangled in psi minus. Presumably you'll say that the entangling event caused them, B and C, to be entangled. Does your causality theory tell you that the fact that A and D are also entangled in the state psi minus, does your causality theory tell you that that entangling event caused that to happen? The answer is yes or no. So just remember your answer. The next step, the final step, is delayed choice entanglement swapping, a sort of example of post-selection. So we prepare the qubits exactly the same as before, except this time we do the quantum tomography data first. And we do the quantum tomography data first on the qubit D as well, maximally mixed. Then we do the entangling operation on B and C so that the quantum tomography data is in the pass light cone of the entangling event. The data goes forward in time, of course, and it'll be maximally mixed. And once again, we want to pick out the sub-ensemble in which psi minus was the result of the entangling operation, send the information forwards in time, construct the state, and it will be in the state psi minus. So at this point, if you said yes, that you believed that the previous slide was an example of causality for A and D, then I suggest that you have to accept retrocausality because we've got the same state in the past. Yeah, so here we're approaching the the experiment at last that I want to describe. If we think about that result and we think about steering, every time we got a quantum tomography result on A and D, the qubit B was, well, talking about A first, qubit B was steered into the same state. Because we're using this special state phi minus, it makes it very easy to explain. It's steered into the same state. And similarly, when the quantum tomography data, whatever it was, sigma x, y, z, was performed on D, C was steered into the same state. So it looks as if B and C are in the same state as A and D, and therefore that B and C are also in its psi minus in anticipation of the psi minus entanglement event. Now that's not a proof, but it's a motivation for the experiment that I want to consider. So the proposed experiment looks like this. I'm going to switch, we do, instead of doing the quantum tomography on A and D, we do the quantum tomography on B and C to see what state they were in, since we suspect that they were steered into the same state. We only need a maximally mixed state for the experiment. So B and C should be in maximally mixed states. But there's no reason why those maximally mixed states should come as the reduced density operator of an entangled pair. So we can have this experiment where we just start with maximally mixed states, do the quantum tomography, do the entanglement, pick out a sub-ensemble in which the result of the entanglement was one of the Bell states, for example, look at the quantum tomography data and see whether it was in a Bell state or not for that sub-ensemble. And there's another big advantage. So just for comparison, that's the previous delayed choice entanglement swapping experiment, and this is the one that we propose. But the big advantage with this one is that we can control the maximally mixed state. The maximally mixed state that comes from one qubit from an entangled pair is in what's called an improper mixture. We don't know anything about the quantum states of the qubits which are making up the maximally mixed mixture. But here we can control that. We can put in qubits under our control. Let's say we produce the ones which go to the left-hand side by equal numbers of pluses and minuses, and the qubits that go to the right-hand side as equal numbers of ones and zeros. So there's an element of control here which is missing from the delayed choice entanglement swapping experiment. So just to go over the experiment again to make sure we have everything in place, and also to put a bit more information into it. We know that individually those measurements will give us a maximally mixed state. Let's also look at the qubits which emerge from the entangling operation so that we can just make sure what's happening with them, do quantum tomography on them as well. They'll also be maximally mixed. Now, the question that we're going to ask ourselves is, what's going to happen? We expect, obviously, that the upper, when we choose the sub-ensemble in which, let's say we get phi plus or psi minus or whatever, we'll say on the next slide, as a result of the entangling operation, we know that the upper state's going to be that entangled state. So the question that we have to ask ourselves is the lower one going to be entangled or not? Let's say we choose the phi plus outcome here of the entangling operation, which makes things simple. We send the information of which runs gave phi plus to the computer data above like that, and it does the calculation and finds out the state phi plus. So that's normal entanglement. We send the data back to the computer which took the original data before the entangling event. It looks like it's going backwards in time there, but of course it's not. We could do this the next day, the next week, the next month. It's just a matter of telling the data which is stored inside the computer, look, discard 75% of the data just keep those particular runs, which I hereby tell you, which resulted in the state phi plus as a result of the entangling operation. And then we can get the computer to do the calculation. Maybe it's going to come up with a maximally entangled state. Maybe it's going to come up with phi plus. Maybe it's going to come up with something else. We have to find out. Now, nobody's done the experiment, as far as I know, although an experiment which is quite close to it has been done, as I'll say in a minute. So in the absence of an experiment, we just need to calculate the result from quantum mechanics. Because we know that quantum mechanics always gives the right result anyway, and so in a way experimentalists are superfluous. I used to be an experimentalist, by the way, so it's not a nasty joke. And I've turned this on its side here just so to make the slide easier, but time's now going across the page. So we start off with a maximally mixed state row. We want to calculate the quantum tomography data. So we'll want to calculate the probabilities of outcomes I and J. Let's just number our quantum tomography data, I, J, K, L, etc. So they're just projection operators. We're doing this just for the set of runs in which phi plus was obtained. We took quantum tomography data again, so we need to calculate the probability of K and L for all the values of K and L for that quantum tomography data. Now, the calculation in the forward time direction is very easy, of course. We just calculate that probability, and that expression there tells us by inspection that the quantum tomography data is going to come up with the state phi plus, that projection operator on the end. And so we know the result there, phi plus. Now, we've got to do the other calculation backwards in time, so we could just simply plug in the two-vector formalism. That would be the simplest way to calculate the probability back there. There's an Australian, David Pegg, whose group has also written down the equations for calculating probabilities like that one. We could plug his formulae in. But it's very simple just using Bayes' theorem to do it ourselves. I've left out the bits on the bottom line, but we really want to just calculate the probability that we get I and J and phi, and divide by the probability that we get phi, which is a quarter. So some numerical factors here will cancel that I haven't put in. But the crucial thing to calculate is that, which is normally nasty. That's the two-vector expression that you would normally be involved with. But here, when we substitute for rho, you can see by inspection what we're going to get, which is that. Exactly the same form as the forward in time one. So quantum mechanics is telling us that the quantum tomography data is going to come up with the same state, phi plus. Like that. Now the reason, as I said, that this is simple is because rho is so simple. It's the maximally mixed case. If it wasn't like that, then we'd have to use the two-vector formalism. We wouldn't be able to switch back to normal quantum mechanics like this. So just going over the experiment again, here we have, if we look at all of the data, we've got maximally mixed states here and there. If we just pick out the results, a set of runs in which phi plus is obtained, then we get phi plus up there. And if we do the same here, we get phi plus before the entangling event. So we've called this pre-entanglement, and the other normal entanglement becomes post-entanglement, if you like. Now I want to dwell for a little while about this because you probably are being polite and not interrupting me at this stage, but you've probably got objections already. But after I say what I think, or what we think is a consequence of this, you're going to be even more resistant to accepting this result. So let me try to reassure you as much as possible at this stage before we go on to something which you might find revolting even. So first of all, let me just note again what the differences here are with delayed choice entanglement swapping, which I emphasise as a well-established concept in the literature. Everybody accepts that as far as I know. The same pair of qubits are involved here, whereas in DCES it's a different pair. I don't think that's very significant. No qubits are entangled at the beginning of the experiment like they are in delayed choice, but I don't think that matters very much at all either. But this business does. They're an improper maximally mixed ensemble is being used, so there's no control of the preparation states, but as I mentioned before, here we have control of the input states, the preparation states, which gives us the result that I just mentioned. We've got to wonder to ourselves, is post-selection okay for tomography? Are we doing something wrong here in post-selecting the tomography data? Is it okay to do it? Well, first of all, we've derived the result using standard quantum mechanics. So if we're doing something wrong here, quantum mechanics should really tell us what it is. The same thing works okay for delayed choice entanglement swapping, as I said. Recently, there's been these fascinating experiments on direct measurement tomography, which involves post-selection. This is one of the consequences of the two-vector formalism that we heard about yesterday. One of the many intriguing consequences of that approach. And so in that method, this is a diagram from the first paper. I just want to note that the sequence is to prepare a system, do a weak measurement, do a strong measurement, and post-select. So if post-selection is no good for tomography, then these experiments have to crash as well, because they're using post-selection for tomography, for in fact directly determining the wave function. And I just couldn't resist putting this diagram up from the second paper there. If you remember the calculations of the quantum potential in the Bohm model that appeared in the literature, I don't know, sometime last century, this is an experimental result which so much resembles the calculations that were done for the Bohm model. Not that I'm advancing the Bohm model. And finally, I want to look at a comparison between pre and post entanglement to see whether they're similar to one another or how different they are from one another. So first of all, do you calculate, quantum mechanics calculates the state as being entangled in both cases. As far as the measurements that go into the establishment of the entanglement, it is true there's a difference. The measurements for pre-entanglement have to be performed beforehand, but the measurements for post-entanglement afterwards. But it would be impossible to establish pre-entanglement unless you did the measurements beforehand. So I don't think that's significant. The measurements are selected after the entanglement in both cases. Quantum tomography tells you what the state is. Well, yes, in both cases. Direct state determination, the ones that are on the previous slide, if you use that method, it would come up with the state in both cases. There's a variation of that called weak measurement tomography that would give the same result in both cases. If you gather data where you could test the Bell inequality for the ensemble as a whole, it would show nothing. It would show, you wouldn't be able to show it was violated, but for this sub-ensemble you would be able to show it was violated in both cases if you took the right data. As far as steering is concerned, there's a slight difference because you'd have to take the data which was suitable to establish that steering had occurred and then select out of all of those measurements the ones that did demonstrate, because that sub-ensemble was, say, 5+. Whereas in the post-entanglement case, you can do it that way, or you can select the sub-ensemble first and then do the measurements. So you don't have to gather measurements on the whole set. I don't think that's important. Perhaps more reassuring, the most reassuring thing about the real existence of pre-entanglement is, can you use it as a resource as you can use post-entanglement as a resource? Now, one of the ways that you can use post-entanglement is for quantum key distribution. And it turns out that what's now called device-independent quantum key distribution, which is an even more secure way of establishing a secure distribution of the keys, is actually relying on this, at least this is a claim that I'm making, the authors don't express it this way. Let me first of all go back to a paper back in 1996 where the delayed choice entanglement swapping was really pointed out could be used as a method of quantum key distribution. And the authors of this paper actually refer to a time-reversed EPR scheme, which anticipates what, to some extent, what I've mentioned in the last few minutes. So in the first picture here, the entangling pair is produced in the centre and distributed to Alice and Bob. So that's the normal way that you deal with quantum key distribution. But they also suggested this possibility that A and B produce qubits and send them to the centre, where the centre would do the entangling. And that's one, more secure, and the authors here were particularly concerned that it would be cheaper and easier to produce a network of key distribution if you did it that way. Now the first diagram, A, remember this was in 1996. If you read the paper, even though they don't mention entanglement here, what they're doing is using the correlations between the A's and B's. But you can see that the authors of this paper had really anticipated delayed choice entanglement swapping in their discussion of A there. But it wasn't until 3 years later that Asher Perez first revealed to the world delayed choice entanglement swapping. And he'd obviously discussed this with the authors because he's in the acknowledgements in the paper. So that was 3 years later. Nobody, looking at part B there, once again, pre-entanglement, in this case, is not being mentioned in the paper, but the correlations between the measurements or the preparations of A and B, given that the qubits are going to be later entangled by the centre, those correlations are being used for key distribution, and entanglement's not being mentioned. And in fact, in a modern experiment, just recently implementing part B there, where the qubits are produced independently on a sort of city scale, Bob and Alice produce qubits and send them to Charlie, who entangles them. Once again, the correlations between Bob and Alice are being relied on in this paper. But the fact that there's entanglement occurring, according to what we say, between the qubits of Bob and Alice is not directly mentioned in the publication. So we could say that pre-entanglement is being announced here so long after this paper, just as delayed choice entanglement swapping was announced sometime after it was actually discussed without using the term in that paper. So I haven't reached the end of the talk yet, so don't breathe a sigh of relief. This is a sort of interim conclusion. The claim is that we've established pre-entanglement, and we've also established, and this is the second half of the talk, that independent preparations can lead to these pre-entangled states. And that raises a problem, and so I want to try to explain what the problem is. So let's say that Alice prepares some states. They needn't all be different. The I there just numbers the preparations. She'll be able to describe the collection by some sort of by a density operator, which will be So let Bob do the same thing, prepare a bunch of states, but let him do it independently of Alice. He'll have a state like that for his. The most important thing is that they're independent. Because they're independent, the ensemble as a whole must be separable, and also any sub-ensemble of states must be separable. Because when you write the expression down for the joint state, you can see by inspection that it's separable, and it'll certainly pass the tests for separability. So that will apply. So the most important thing is that the joint ensemble and any sub-ensemble of states prepared by Alice and Bob in this way are going to have to be separable, according to the understanding. But let Alice and Bob prepare those states so that they're maximally mixed. Let's look at the sub-ensemble for which later, subsequently, the state phi plus is obtained. Our pre-entanglement argument shows us that the state of that sub-ensemble is the pure state phi plus, which contradicts separability. So that's the contradiction that I want to talk about. I flipped onto the next slide too quickly. I want to just mention two improprieties here. We're not sort of getting into an R-rated section of the talk. This is the diagram that comes from this paper, Proper and Improper Separability by Timson and Brown, which I think's an interesting paper. And they mention that the contents, this sort of discussion is sort of a bit neglected by the Foundations community because the problems that this sort of raises are not often addressed. In any case, if we have a mixed state, we can have a proper mixture where we know, and I'm going to contradict myself in a few minutes about saying this, but in any case I'm going to say it because it's a common understanding at the moment. In a proper mixture, you're able to identify the states of the constituents of the mixture, whereas in an improper mixture, you just can't do that. The best example of an improper mixture is just one qubit out of an entangled pair. But if you have a proper mixture, the mixture can obviously be separable or entangled. But the difficulty is that you can take a bunch of entangled states and mix them together, form an ensemble of them, and the ensemble as a whole will be separable, which sort of is very funny. And so in this, that's the meaning of proper and improper separability. If it's properly separable, then all of the sub-ensembles of the ensemble will be separable as well. Any sub-ensemble that you can pick out. If it's improperly separable, then you're able to pick out some, not pick out in a normal way, some entangled sub-ensembles, even though the ensemble as a whole is separable. So in terms of this, we've really proved that a properly separable ensemble can be decomposed into entangled sub-ensembles. So the situation's even worse than the one I mentioned before. In any case, if you find that confusing or my explanation of it confusing, it's not an important point as a whole for the talk. So just to go over the situation again very quickly. For the set of runs that give phi plus, we have the state phi plus in the future, of course, but we also have the state phi plus in the past. The problem is that if we buy the separability of the input states in this diagram, we can't get phi plus for the earlier state. It must be separable. Whereas for the case that we've calculated the results for phi plus, we do get the entangled state here and we do get the entangled state there. And so we have this contradiction between the argument from independent preparation and the argument from for pre-entanglement. Just let me mention at this point different ways of selecting a sub-ensemble from an ensemble that we've seen so far. The first was just remembering how we prepared. The second was by steering. And now we've got another method, which is the pre-entanglement method of picking out a sub-ensemble. Now what we want to say is that this drives you, forces you, you have to wriggle a lot to avoid adopting an ensemble interpretation of quantum mechanics. So here, let me not shy off from saying that instead of saying, look here, you ought to accept the ensemble interpretation because I like it, we're trying to say, we're claiming that you have to accept it. Otherwise you won't be able to live with the results of this experiment. That's what we're claiming, at least. So let's be upfront. Now let me give a few quotes about people. I put ensemble in inverted commas here because Perez wouldn't say that he adopted an ensemble interpretation explicitly. He's got sort of a technical objection only, though. We are thus led to the conclusion that the psi symbol, the so-called state or wave function, is not an attribute of a system, but of a procedure, I would say an ensemble. A single physical system has no state. One might be tempted to say that a system prepared by a procedure psi is in the state psi. However, this seemingly innocuous phrase leads to paradoxes, which he then explains. Since everybody else says that Einstein's on their side, I don't see why I should be the exception. So here's a quote from Einstein. The function psi does not in any way describe a condition which could be that of a single system. It relates rather to many systems, to an ensemble of systems in the sense of statistical mechanics. And then going back to Perez, because he always explains things clearly, a quantum mixture is therefore radically different from a chemical mixture, which has a unique decomposition into pure components. And here's another thing which gets ignored. If you have a density operator rho, you can decompose it in lots and lots of ways into other density operators. Here, rho 1 and rho 2. Somebody else can say, no, I prefer rho 3 and rho 4. And there's no way of telling any of them that they're wrong. But we say that has no physical significance, the fact that you can do that. We say, well, I'll come back to that actually on the next slide. I haven't mentioned many other people who've defended or advanced the ensemble interpretation. Notably, Ballantyne is the most recent proponent. And one ought to at least compare it with Bayesianism. A Bayesian, of course, wouldn't countenance an ensemble interpretation, but in many ways, their picture is similar to the picture that I'm going to describe here. So the claims are subensembles don't have constituents with quantum states. Systematically selected ensembles, they're the only things that have states in quantum mechanics. And by systematically selected, I mean that you don't go to the data and sort of pluck out by hand some subensemble in some state. I mean, you do it in a physical way. You're able to select the same ensemble in the same way each time an experiment's repeated. So it's not an artificial thing, it's a physical thing. So comparison of the old and new. The standard picture, which I have to keep on telling myself not to fall into now, because I certainly would have taken this position before. The standard picture is to say, well, if you prepare some zeros and ones and put them together in an ensemble, then you've got a bunch of zeros and ones. Here there are 6 zeros and 14 ones, and so we'd say that the state here really is 0.30 and 0.71. And we would say that the fact that you can write it in other ways is just a mathematical accident with no physical significance at all and something we should just forget about. Now, it is true that you can partition that subensemble, that ensemble, given your knowledge about the preparation, into 2 pure states. Once you've got a pure ensemble, then there's only one way to write down its density operator, and there can be no argument that those 2 subensembles. We can't rule out that those 2 subensembles are like that. But we see that there are different ways of partitioning an ensemble, as I've mentioned. So here, if we prepare, so on the ensemble picture, at least the variation of the ensemble picture that I'm advancing, Ballantyne probably wouldn't agree with it exactly. If we prepare some zeros and ones to give a row, all we've got is the row. We certainly can divide them into zeros and ones if we remember how we prepared them. But if we use another way of partitioning the ensemble, we can prepare 2 subensembles in entirely different states. And that's what we do when we've established the pre-entanglement subensembles earlier in the talk. Partition the ensemble in a different way so that it's not in the states that were the prepared states. So the upshot really is all ensembles of non-pure states are improper. You don't find out about them until you can partition them into pure states. And just checking the time, I just want to say a few words about a discussion which is relevant to this in a popular science book, The Evolution of Physics by Einstein and Infeld. And here's the quote: "In the kinetic theory of matter, we have the statistical laws governing the aggregation gained on the basis of individual laws. But in quantum physics, the state of affairs is entirely different. Here, the statistical laws are given immediately. The individual laws are discarded." Well, I guess they're not actually discarded, but they're not available to us. "Quantum physics abandons individual laws of elementary particles and states directly the statistical laws governing aggregations." And they go on to discuss this by way of an example, which I think is illuminating. They say in classical physics it's like a two-storey house. The lower level, in modern terms we'd say, is the ontic level. The upper level is the epistemic level, or the statistical level. And you can go up and down that staircase between the two levels. So you can think about the epistemic state in terms of an ontic state. You can think about a collection of ontic states in terms of an epistemic state. So you can go up and down the staircase freely in the classical case. But in the quantum case, we only have the top story. We only have the statistical theory. We have no ontic theory. And Einstein and Infeld say it's worse than that. You can see the beginnings of a staircase there. But they say that staircase is useless. That because we've come in at the statistical level, actually we're not going to get we're not going to be able to squeeze anything out of that statistical theory to tell us what's going on at the ontic level. And I think we know that Einstein tried to get in on the ontic level by ignoring quantum mechanics and going a different path. And I think if you read that section of the book, you get some idea about why he did that. I emphasise it's at the popular level, so it's maybe reading between the lines a bit to say what I've said about it. So there's probably time for me to say a few quick words about the ontic epistemic discussion recently. Here I take two diagrams out of the famous PBR paper, which just shows you how influential it's been in the literature. The only thing I really want to say about it is that in this scenario, in this ontic epistemic discussion, the idea is that the qubit has got an ontic state, so we're an epistemic and a psi. So here we're not looking at this as an ensemble picture. We're looking at it in that terms of picture. And what we're saying is that you ought to look at it in those terms, in which case you need to revisit, we're saying, the ontic epistemic picture. And one could also contemplate doing the PBR experiment, starting off with maximally mixed states. Here Alice and Bob could randomly do 0, 1, plus, minus measurements. To deal with the case, the PBR case, where you've got 50% overlap, they just chuck away those results and send forward the results where either one of them got zeros or pluses. Sometimes Alice would send a qubit forward and Bob wouldn't, but the experimentalist has got to deal with it, so they only take into account the case when those four states go forwards. And then there's an entangling operation, and 0, 0 is in red there because it's orthogonal to that one of the entangling states, and each one of the other three are orthogonal to the others. So the problem now is, because of our introduction of pre-entanglement, we say that the independent preparations of Alice and Bob, even at the quantum level, see the top left-hand corner, even at the quantum level, we can pick out a pre-entangled sub-ensemble here. So the idea of independence here is really questionable. It's not just questionable at the ontic level, it's questionable at the quantum level. So I can just skip. I've come to the end of my time, I think, if I leave sufficient time for questions. So there's no need to go over this slide very carefully, except to say that, just to emphasise that delayed choice entanglement swapping, is a well-established point in the literature. So, and this is a recent paper by the Zeilinger group just proving that the quantum tomography data can be taken in the past light cone of the entangling event, which requires some good experimental tricks. I don't think we need the rest of that slide. And this is just a summary of the fact that we're saying that only ensembles can have states. And I'll skip this slide as well because I want to leave some time for discussion. That's just speculation. So the conclusion is that pre-entanglement exists. It should be checked by experiment, of course. Sub-ensembles have maximally mixed. Sub-ensembles of maximally mixed independently prepared sources are not separable if they're subsequently subject to an entangling measurement. But they must be properly separable if individual systems carry quantum states around with them. The conclusion is the only things which have states are ensembles or systematically and reproducibly selected sub-ensembles. And some claims are measurements have retrospective effects if sub-ensemble states can be chosen from their outcomes. The current ontic epistemic discussion needs to be revisited because qubits, quantum systems, don't have quantum states. And we query ontic preparation dependence because of pre-entanglement even at the quantum level. So that's the end of the talk. Thanks very much.